calculus derivation. Okay, you got A equals constant, right? And dv dt equals A, which means then that V is your general antiderivative of A with respect to t, which is AT plus some constant. Okay? Now, this constant is just whatever the velocity is when t equals 0. And let me write this velocity as a function of time. Okay, because that's what it is. We've got a function of time here, right? C clearly equals V at time t equals 0, because if we plug 0 in for t, we get V of 0 equals C, right? So C is V of 0. So we could write V of t equals AT plus V of 0, whatever your t equals 0 velocity is. Okay? Then, dx dt equals V. So x of t is your antiderivative of V of t, right? General antiderivative then of AT plus V of 0 with respect to t. And that antiderivative is 1/2 AT squared plus V of 0t plus another integration constant. I've disposed of this one, so I can still use C down here, but it's not going to be the same as it is up here, right? Because that's how we treat integration constants. Where C equals x of 0, because if x of 0 is a position at t equals 0, then x of 0, we plug in 0 here and 0 here, and we get C, right? So x of 0 equals C, so C is x of 0. Okay? Now this gives us two equations. Should have put the box all the way around the x of t. Okay? And these equations are totally consistent with these equations. Okay? The only thing that's a little different these are totally consistent with the previous equations. If VI equals V of 0, instead of VF you use V of t, and instead of delta S, well that's, let's go ahead and write it as x of t minus x of 0. Okay? Now I'm going to kind of let you reconcile that. I'm going to point out every detail of it because you've got to think about it. But all this is how far you've gone since you started, right? Okay? Here we assume you don't care where you started. This is how far you went. It means the same thing. Okay?